view data and also how to manipulate it and save it afterwards. So that's what the practice about today. But the tool that you're going to be using for this is called CASA. It's the most commonly used radio astronomy software out there, I think. It's not the best, but it's the most widely used. And yeah, it's a set of like C++ code, which has been bundled with Python in a very funny way, but it kind of works. And yeah, so that's what most people use when they do it. So probably every radio image you see in CASA in one way or another. So basically, like the main thing about CASA is the format in which the visibility data is stored, and it's called basically. So these are called CASA tables, and they are just directory structures where you have all the metadata of the data set stored in this. I wouldn't say it's efficient, but it's a very robust system. Not the best, but again, it kind of works, and this is what everyone uses, I think. And when you take this format and you put visibility data into it, we call it a measurement set. And like 9 out of 10 times when you get visibility data, it's going to be in this format. So it's a good idea to know how it's structured and how the data is stored and how to access it and how to manipulate it and so on. So yeah. So that's it. You could do all that through CASA. Okay. So basically, in this database, it's basically just a database of data, where all the data that you have and all these attributes are stored in columns. So, for example, here you have all the you have antenna 1 as well. But so there'll be antenna 1 and antenna 2, so it's basically all the data collected by that baseline. So you have that antenna 1 and antenna 2 pairs like that. So that's all the baseline information. And so in the data column, obviously that's where the data is just kept. So this way you find your data. This is the exposure for each integration that you have. So this is a 10-second exposure. And you have all these other things that tell you about the data set that you are looking at. So this is the basic structure of these things. Okay. And basically, so CASA has like a whole suite of tasks to do all different things for visualization, imaging, processing data, flagging, calibration. It's really like this all-in-one, really massive thing that you use. So once you are in CASA, all you need to do is basically just type, run the command task list, and it gives you all the tasks that you can perform in CASA. And if you need help, like a brief summary of all the tasks, and what they do is run task out. So to again list all the tasks, but like brief summaries of what the tasks do. And if you need like detailed help on any task, it's help, and we give the name of the task, and you bring out very detailed help. Actually, in CASA, the one thing that they do very well is they document all their tasks in a very good way, which is really vertical. So this is like just a list of all the tasks that you can have in CASA. So you have tasks for calibration, for modeling, imaging, analysis. It's a whole slew of things. As you can see, there are many these things. And we're using, I think, maybe 3 or 4. Okay. Yeah. The CASA is very, it's not, I wouldn't say it's dangerous, but it's like, it can lead you to fairly elaborate rabbit holes if you're not careful. So you should always be careful with use CASA. This is a code from someone probably who has used CASA mostly. Yeah, always be careful. Okay, so about the practice again, just a brief overview. So we have some CASA data that you're going to be just viewing just to see how the data looks like. And then after that, you're going to try to identify like bad data points in the data, basically data that has been contaminated by RFI. It's like a little blurb of what RFI is. And yeah, so we're going to try and plan the data out and see how that improves the data that we have. Okay. So just to give you like a short description of what the data is. So the data has so it's an aggregation of 3 fields, right? And this is basically the UV coverage plots of all the different fields. So, but it's from the same instrument at more or less at the same time. So there's a complicated on why the UV coverage is different for each of them. So basically, this is the UV coverage for 3 fields, which are observed at the same time with Cat 7 on the same day, but somehow the UV coverage is different. Anyone know why? Sorry? Different times? No? That could be, but no. It's time. Sorry? No, field of view doesn't affect the UV coverage. So what does the UV coverage depend on? What's the
baseline and wavelength?
Baseline and wavelength? Yeah. And? So this is at the same frequency, so the wavelength is the same, right? And it's the same baseline as well, right? Because it's the same antenna coordinates. So what's the other thing?
Look on the sky.
Sorry?
When you look on the sky.
Yes, exactly. So naturally, the declination for these sources is different, and the UV coverage will be different because the declination is different. But you can tell just by looking at that maybe the declination for field 1 and field 2 are similar because the UV coverage is almost kind of similar, right? So basically, yeah, these are the kind of things. All right, let's move on. And I don't know, it's not an impressive plot, but when you do it yourself, you get to appreciate it. And this is just basically the amplitude of all the visibilities versus time for all the different fields, for all the frequencies, and for all the baselines. And it doesn't look very good, right? So there's all this point to go really high. You don't really trust these points are from the sky. So you want a way to get rid of those. Also, that's something over here. And there's also like a slew of data points which are kind of hidden down over there. And our task today would be just to try to identify all the bad points and try to get them out. So and that's basically